Hello everyone. In this lecture we will be beginning with a new chapter, that is gaseous state and thermodynamics, and we will learn various concepts about gases, what is pressure, etc., evaporation, etc., like this, fundamental things about gases, as well as what is basically known as thermodynamics, etc., and we will learn some various physics concepts in it. So, and we will learn how to solve questions based on them. So we'll begin with the chapter. So it has basically two parts. First is gaseous state and the other topic is thermodynamics. So it is basically divided into two parts, gaseous state and thermodynamics. Okay. So first, gaseous state. So there is a fundamental theory basically behind it, that is gaseous state means we are dealing with gases. Okay. So we are dealing with the gaseous nature of the elements. So when we deal with gases, there is an important theory known as kinetic theory of gases. Okay, which we generally use in order to deal with the model of gases. Okay, so what this theory is basically about, that gas is nothing but, as we know that whenever you give a container to a gas, whenever you fill in a gas in a container basically, so if this is a box A, you have a gas in it, so the gas occupies all the volume in it. Okay, so it occupies the full box A. This is because there is a very weak intermolecular forces between the molecules of the gas. So basically the molecules spread randomly into the box and occupy the space of the box. Okay, so this is generally the molecular nature of gas, that it occupies the whole volume and space provided to it. Okay, so there are few assumptions in this. So few assumptions of kinetic theory of gases. That we need to be familiar with in order to understand this kinetic theory of gases. Okay, so I would not write down each and every assumption, but the important ones. Okay, so first of all, the thing is, the molecules of gases are rigid, perfectly elastic, and solid spheres. Okay, so what do we mean is, basically they are spherical in shape. Perfectly elastic means whenever a particle collides with a wall, it rebounds with the same velocity. Okay, this is known as elastic collision. There is no loss of energy basically in a collision. Okay, and second is basically in this only the inbound assumption is the size of particles is very small. Size of particles is very small. So basically, almost zero volume is occupied by them. So we assume that they are very small in size, but so the volume occupied by the molecules is zero. So if I say that what is the volume available for the molecules to travel to occupy is basically V only if the volume of box is V. So we are excluding the molecule volume, that is, as they are spherical, you can find the 4 by 3 pi r cube is the volume of one molecule, and you sum up the molecules, then you will get basically the volume of the total number of molecules, but you are saying that volume of the molecules is negligible, so we take it 0. Okay, so this is the major assumption in it, kinetic theory, that there is basically zero volume occupied by the molecules of the gas. Okay, and the second assumption is that molecules are in continuous random motion. Okay, random motion is that the motion does not have a dependence on some other variables. Okay, so they are basically moving in all directions with all possible velocities. So there is basically no uniformity or specificity in the pattern of the velocities. Okay, so they are moving in. So basically, if the box is containing the gaseous molecules, a gaseous molecule can be moving in any of the directions. Okay, so the molecules are moving in each possible direction and with each possible velocity. So there is no specific pattern that yes, the molecules are moving in the right hand side direction only with specific velocity. It's nothing like that. They are completely random. Okay. And the third assumption there, when the molecules collide basically with one another or with the walls of the vessel, at the time of the velocity, their velocities change both in magnitude and direction. However, in the steady state, the molecular density remains the uniform throughout the gas and does not change with time. I would try to explain this. What does it mean? So the third assumption is that the molecules during their motion collide with each other and the walls of the vessel at the time of collision or at each collision, their velocities change both in magnitude and direction. However, in steady state, the molecular density remains uniform throughout the gas and does not change with time. So this is the third assumption. It says that whenever there is a molecule traveling in this box, let us suppose there are gas molecules. If the particle is moving, gaseous molecule is moving in this direction, there are many particles moving in all different directions. So it is possible that two of the molecules collide or the molecule collides with a wall. Okay. So during a collision, the direction of the molecule obviously changes. Okay. So the velocity first decreases or increases and changes its direction. That is basically what is referred over here. That at each collision, their velocity change both in magnitude and direction. Okay. That is pretty obvious. However, in steady state, the molecule density remains uniform throughout the gas and doesn't change with time. This means that when the gas is in steady state, that means it is in a uniform state. No process is taking place on the gas. What happens is basically if a molecule changes its direction like this, when it was going in a direction like this, if there is a specific change in the direction of the molecule, there is a reverse change in the direction of another molecule. So basically the total state of the system remains same. That remains constant at each and every time. Okay, that is mentioned that however in a steady state, the molecular density remains uniform throughout the gas and doesn't change with time. So basically there is always in a steady state, there is a uniform state of the gas that is maintained. Okay. That's why it is referred as steady state. Okay. The fourth assumption says that no forces of attraction or repulsion are exerted on the gas molecules by the other molecules or the walls of the container except during the collision. Okay, so basically it means that all the particles are free of each other. Basically, if one particle is moving like this, one particle is moving like this, they do not interfere in the motion of each other. That is, this particle A and this particle B are independent of each other. They do not exert any force on each other, neither attraction nor repulsion, nor the walls of the container exert any pressure. So one thing you can infer from here is that energy is all kinetic in nature. That's why it is known as kinetic theory of gases, because there is no potential energy being involved in it. Only energy involved is during the collision. When there is a change, then there is an interaction between two particles directly. Okay. The fifth assumption is collisions are purely elastic. And as I told you, that is, what is a purely elastic collision? That energy of the molecules remains the same before and after the collision. So the important thing over here is before and after the collision. It is not saying that during the collision. That means that the first scenario before the collision happened and after the collision had taken place, the energy is same. During the collision, there could be some change. So if it was a molecule, this was a molecule traveling here. So the final nature of the energy of the molecules would remain same. During the contact, there could be some changes, but before and after, the energy would be conserved. Okay. And in between, the changes happen because in that we assume that there could be some energies being involved. So that changes the direction and the various other concepts. Okay. The sixth assumption that is made is molecules travel in straight line. Straight line with uniform velocities in between collisions the average distance traveled by a particle or a molecule between two successive collisions is called mean free path of the molecule. Okay. So basically, and we assume that time during collision is 0. We assume that the collision takes instantaneously. So there is no time involved during the collision. Okay. So these are the basically assumptions that are made in the kinetic theory of gases. So basically there are 6 assumptions. First, that the particles are rigid, perfectly elastic, solid spheres, and the volume occupied by them is almost 0. Then says that the continuous in random motion of the molecules. So the moving in all possible directions with all possible velocities. The third assumption says that there is the molecules may collide with each other or the walls, but the velocity where the velocities change in both in magnitude and direction, but at a steady state there is a uniform distribution of the molecules and their velocities. Okay. And the fourth assumption was there is no force of repulsion or attraction between the molecules, which ensures that all the energy in the gaseous nature is kinetic only. The fifth was the collision are purely elastic, which says that the energy is conserved before the collision and after the collision the energies are same. Then the sixth assumption was that whenever there is no collision, the particles are traveling in a straight line with a uniform velocity. Okay, and basically the distance between two successive collisions is known as the mean free path of the molecule. Okay, so these assumptions are basically a definition for being a ideal gas. Okay, so a gas that satisfies ideal gas, or we call it perfect gas. Okay, so a gas which satisfies all the above assumptions of kinetic theory of gases under all conditions of pressure and temperature are basically known as ideal gases. So it is basically these assumptions are a set of definitions for being a gas, for a gas being ideal gas. Whichever gas which satisfies all these assumptions under all conditions of pressure and temperature is basically known as an ideal or a perfect gas. Okay, but there is ideally no perfect gas or ideal gas known till now. All of them are real gases and they deviate from these assumptions at some or the other conditions of temperature and pressure. Okay, so this theory, kinetic theory of gases, which says that yes, in the gases there are very much there is a lot of molecules of the gases which are randomly moving, and this, what are the, basically you had made some assumptions and we say that yes, this is a kinetic theory of gases. What are the proofs that yes, actually the gases have such kind of properties? So what are the basically proofs in the support of this assumption? Okay, so there are some evidences in support of molecular motion, because the essence of this kinetic theory of gases was that gases are basically consisting of various molecules which are randomly moving and whose velocity patterns are basically known, which is steady in the steady state, maintain a particular uniform motion distribution. Okay, so that you have to find evidences to that. So one of the evidence is diffusion. Diffusion is nothing but basically the particles of one substance diffuse into another against the effect of gravity due to the molecular motion because if there would not have been a molecular motion. Two gases would not have combined or basically diffused into each other. Okay, and the example is basically hydrogen gas diffuses into CO2 gas when a jar filled with H2 is held mouth to mouth over a jar filled with CO2. The H2 is lighter than CO2. So basically, if you put a test tube filled with H2 mouth to mouth with a test tube filled with CO2, H2 is lighter than CO2, so H2 must remain in the upper column only and CO2 must remain in the lower column only. But it doesn't happen like this. What the final result is basically the mixing of both of them. You have H2 in the whole column, similarly CO2 also diffused in the whole column. So that is just because of the molecular motion. This is possible only when the molecular motion exists, that there is no uniform direction of motion and there is the random motion of all the particles. Then only there could be a perfect diffusion of both the gases. So this is one evidence in proof of the molecular theory. The second proof or the evidence in favor of the molecular theory is evaporation. Evaporation is basically a phenomena which you have seen many of times. Your clothes dry up in sunlight just because of evaporation only. Evaporation basically involves, it is a process of escaping of fast moving particles or molecules that are basically having higher speed than the average speed this basically results in lowering the average speed because the higher speed molecules have gone out. So there is decrease in the total speed. So there would be a decrease in the average speed of the molecules as well, which in turn lowers the temperature producing a cooling effect. You would have seen this effect quite often because in summers, like, you sweat a lot, and when the sweat evaporates, you feel cool. That is the process because evaporation is the process of escaping of fast moving particles. As we told you that in the kinetic theory of gases, that there are particles moving in all possible directions with all possible velocities. So there is an average velocity of the whole set of molecules in a gas, and there would be some particles moving with a very high velocity, some moving with an average velocity, some moving with a low velocity. So it is the basic evaporation is the phenomena of escaping of the fast moving particles that in turn brings down the average velocity, and the average velocity is directly proportional to the temperature. Okay, so as the average speed is lowered down by the escaping of the high energy particles or high velocity particles, which lead to the lowering of the temperature as well, thus producing a cooling effect that we generally observe while the sweat evaporates. Okay. The third in the support of this molecular model, the third evidence that is in support of this molecular model is basically known as Brownian motion. The example of this is basically motion of smoke particles in air. You must have seen in canopies, when there is a canopy in the forest, or you have seen that in sunlight you can see the dust particles moving randomly here and there. That is basically known as the Brownian motion. That is also in the support of the molecular motion, because that can happen only if the gaseous molecules are in the molecular gaseous molecules are randomly moving. That is what is sent by the basically the kinetic theory of gases. Okay. So basically, as we discussed, our ideal gas is nothing but a gas that satisfies all and each and every assumption that is given by the kinetic theory of gases. So there is an ideal gas equation corresponding to an ideal gas. That is an equation which every ideal gas follows. Okay. Ideal gas equation says that for n moles of an ideal gas, at a pressure P, absolute temperature T, which is nothing but temperature in kelvins, occupying a volume V, the following equation should hold. It says that PV is equal to nRT, where P is the pressure, V is the volume, T is the temperature, absolute temperature, N is the moles of the gas, and this R is a new quantity, which is the most important quantity over here. This is the basically R is the constant, ideal gas constant. Okay, so if we divide basically this N is the basically total number of molecules. If we divide it by the volume, what you would get is pressure. And one thing we know is what is basically density. Density is nothing but mass upon volume. Correct? So if we we can transform this into P into M equals to density into R into T. Correct? So this is another form of the equation, where M is the molecular weight and D is the density of the gas. So this is basically the ideal gas equation, which says that given an n mole of gas, it's occupying a volume V under pressure P and T. This equation should hold that PV is equal to nRT, where R is the ideal gas constant, which have a value 0.081, R equals to 0.0821 in atm liter mole Kelvin. Here R has such a value. So it is basically in the not in the SI units. This is a unit where this is R's unit when P pressure is given in atms, atmospheric pressure, volume is given in liters, N is given in moles, and temperature is given in kelvins. Then this value of R holds. So this in this lecture we learned what is basically the assumptions under the kinetic theory of gases, and we learned what basically being an ideal gas means. that it satisfies all these assumptions, that there is only the particles are spherical in nature, there is no basic interaction between the molecules. And we learned what are the various evidences that actually, yes, gases follow this nature, at least at some pressures and some pressure and temperature conditions, not at each and every condition. Those, because there is no ideal gas in actual, there are some real all the gases are real gases, but in certain conditions they behave like ideal gases. Okay, then we understood what is the ideal gas equation that a ideal gas must hold. Okay, so that's all for today's lecture. In the next lecture we will learn about root mean square, different types of velocity ideal gas should have, and we will understand more about kinetic energy of molecules, etc. Thank you.